I'm Juan Benet, and you're listening to The Changelog.
Welcome back, everyone. This is The Changelog, and I'm your host, Adam Stacoviak. This is episode 204, and today, Jared and I talked to Juan Benet, one of the developers behind IPFS, the Interplanetary File System. Beastie Boys comes to mind right about now. It's a new hypermedia distribution protocol addressed by content and identities. We talked about what it is, how it works, how it can be used, and how it just might save the future of the web. Our sponsors for today's show are TopTal and Linode. Our first sponsor of the show is TopTal. I talked to Daniel Reed, head of design, about their recent expansion to TopTal designers, doing for designers what they've done for engineers. And I talked to Daniel Reed about what was behind this, why designers should be excited about it, and this is what she had to say. Take a listen.
As a designer, or as any kind of creative person, the big overarching question is always like, how can you find inspiration? And for me personally, and for a lot of creatives that I've spoken to, it's really about traveling, exploring, and being accountable for your own career. And I think as a top-tile designer or a remote designer in general, the ability to be able to switch up your lifestyle, change contexts, meet new people, have new ideas that are infiltrated into your life by having that freedom and flexibility is something that's absolutely fundamental to doing great work. A lot of the most talented designers, and again, it's subjective, but a lot of the great ones I see are based in really interesting places throughout the world and travel regularly and have clients who actually promote that lifestyle as well. So I think like for any designer that is wanting to pursue their skills, to be accountable for their life, to have new challenges, that's the real power of TopTal, I feel. You're not just stuck with one product, one company, or even one agency, but you can choose to work on multiple occasionally or a range of different clients. And I think that keeps you fresh. It gets you involved in new technologies, different people, and is really fundamental for being sort of switched on as a designer.
All right, that was Daniel Reed, head of design for TopTal. To learn more, head to toptal.com/designers. That's toptal.com/designers. Tell them the Changelog sent you, and now on to the show. All right, a fun show lineup today. We got Juan Benet on the show. Interplanetary, Jared. We almost wanted to open this show with a fun song, and this is a topic you brought up, IPFS. Why was this on your radar?
Well, I mean, I think first of all, it stands for the Interplanetary File System.
Right.
Great name.
Right.
Just catches you right there. You know, a permanent web. It's just kind of an audacious goal. It seemed cool. It seemed kind of tantalizing, and yet I didn't get it exactly, and so just very interesting. I think, Juan, you may have missed just slightly on the name, because if you would have went with Intergalactic File System, then you could have hopped on the Beastie Boys chain and had Intergalactic File System, Intergalactic. But Interplanetary, it just doesn't quite fit right.
Yeah.
Do you feel like that was a missed opportunity?
Yeah, I definitely. And, funny you should mention, because Intergalactic actually is technically a better name for the original purpose of the name. So the name comes from, it's an homage to J.C.R. Licklider, who came up with the concept of the internet. And the internet, believe it or not, actually stands for the Intergalactic Network. So Intergalactic Network. So that's what the internet stands for. So IPFS is meant to be the file system for the Intergalactic Network. And so, yeah, Intergalactic File System might have been a better name. The original name was GFS, Galactic File System, but then that clashed with a whole bunch of other file systems called GFS.
You guys have pretty good, you got a good name out there and people are interested, but it might not be too late if you want to hop on that.
Yeah.
I don't know if igfs.io is available, but worth checking into. So I guess enough about that one. Let's get to know you a little bit. We like to hear about the origin stories of not just the projects that come across our radar and come on the show, but the people that are bringing us those projects and why it is that you are, somebody who's involved with IPFS and kind of where you come from to get to where you are here today. So can you give us your origin story and tell us kind of where you're coming from?
Yeah. So, man, origin story. Don't even know where to begin. So I think perhaps like the most relevant thing to mention is I pretty much grew up in the internet, so most of my thought has been learning through things like Wikipedia and things, books online and all that kind of stuff. I certainly, of course, went to school and all that kind of stuff, but I very much am a product of the internet generation, and I tend to think about the world of bits often more than the world of atoms. So I, for a long time, I've been very interested in how information moves around the network, how distributed systems work, um, how to make information more reliable and usable to humans. And really, I've come to look at programming as the ability to create superpowers. So not just to have a superpower as a programmer, but to also be able to create superpowers and gift them to other people. Like when you write an application, you're really creating something that becomes this powerful thing, like this, kind of like a magical item that you then give out to other people. And you can give it not only to individuals, but you can give it to billions of people on the planet all at once. And that's huge, right? You think about
That's huge. Yeah.
the people making Wikipedia and how much of a valuable contribution they made to humanity. And that's, a superpower that you can give out to everyone. And so I tend to think about that kind of stuff, how knowledge grows, how we can build better, how can we make these superpowers more resilient? How can we make sure that when you give out the superpower, you're not accidentally making people depend on something that may go away? And more concretely and more grounded, I studied distributed systems. I studied computer science. A lot of both theoretical and applied work. So not just building applications, also thinking about them more deeply, but also not just lost in abstractions. Having to build something that is usable to regular people helps you translate really good ideas from research all the way down to something that's valuable and usable to average people on the internet that may not even care about the underlying things, right? So at the end of the day, most people, when they use the internet or the web, they're not thinking about how information moves. They're just manipulating they're pressing buttons on their computers and clicking on things on the web and learning how to use those interfaces. And so giving people good metaphors for manipulating digital objects is a big part of the whole thing. Like how can you make contributions that are good theoretically and good from where distributed systems theory is going, but also expose that kind of the way to manipulate and create value directly to the user in an understandable way, right? So things like this shows up in interesting little bits and pieces of interfaces, right? But for example, how mail clients will operate, like when they refresh, when they download new mail, when you know that a mail is being sent, when you have confirmation that somebody has read something, right? Like read receipts are a very interesting little thing that it's actually like a very nice distributed systems problem that can help change how people communicate.
So you say you grew up in the age of the internet, and to me, I get that, but I don't get that because I'm 37 and I didn't grow up in the age of the internet. And having the thought process you just shared, you had to get that from somewhere. So I'm kind of curious. When we have people on this show, we're always interested to find out, like, what it was that got them into programming, what hooked them. Sometimes it's games, sometimes it's cheating at a game, sometimes it's doing better at math. Who knows what, but something got you into software. What was that for you?
Definitely games. So I was born and grew up in Mexico, and then I moved to the US when I was 15, and I was playing video games from an early age. Lots of RPGs, for example, and I got really interested in making games. Also, I think the direct reason I learned how to program was that I was part of like an online guild in, I think, StarCraft. I think it was like StarCraft and Warcraft. And we needed to make a website. So I was like, fine, I guess. I mean, how hard could this be? I'll figure it out. And that just exposed me to making websites and programming. And that was like the opening of the rabbit hole. And I think I must have been like 12 or 13 at the time. I don't know. I was pretty young. didn't start as early as some other people out there did, but and for a long time I was just kind of looking up things, copy pasting, not really understanding what I was doing. A lot of trial and error, right? Like kind of like the early version of Stack Overflow programming, but more a yeah. Over time, I started. It wasn't, I guess, until I went through college that I got a really good grounding from like a theory perspective of like how computation actually works, what's really valuable and useful, like good ways of thinking about it, and so on. So I think, yeah, it was hugely valuable to have formal training and understanding, right? So I think you can definitely self-teach a lot of programming and how to make applications and all that kind of stuff, but to really understand the deep um, ways in which these applications behave or how large systems scale and all that kind of stuff, it is very useful to have a formal grounding. And that doesn't mean, go to school or anything. It just means you could read a textbook. You could just, the point is to study it. And I think most people don't get, at least when I was learning, that wasn't as accessible on the internet. I think it's changed. I think there are a lot of really nice tutorials now, and things like edX or Coursera that do give you the experience of a more theoretical class.
Yeah. The distribution mechanism of how we educate around software is changing or is fluid, but the education itself is still just as important as it ever has been. Especially if we're
Yeah.
don't want to be doomed to repeat the failures of the past, which tends to happen when you don't know about the past. So you got the education, you were interested in computer science, and then you got you learned the underpinnings, so to speak. And now here you are leading a group of people coding this new hypermedia distribution protocol. Can you tell us about IPFS, where the idea came from, how it started, the genesis story of this project?
Yeah. So the genesis story is a bit long, or not necessarily long, but there's a lot of things that came together, right? So on the one hand, I was always interested in distributed systems, like that was my focus. In when I was in school, I was very interested in peer-to-peer systems, right? So I was always very interested in multiplayer games and things like BitTorrent and how you could build very nicely scalable systems by sharing the resources and bandwidth of different peers in the network. And a an annoying thing about studying networking, in university, was that they did mention things like BitTorrent and Skype and so on. Like that definitely came up, but it came up in a very cursory level. Like we kind of just discussed it a bit and didn't really take up all of the improvements that were, brought through those technologies into consideration as much. And it took me a while to understand why, right? Like, and the reality is that a lot of these systems are kind of special purpose. The contributions are pretty specific, and they get something working really well for that one use case, but it doesn't translate to nice libraries that people can use for a bunch of other stuff. And you actually have to work a lot harder to get that working, right? Like to make nice interfaces and nice libraries for a much more general set of use cases, which is what people like, teaching and or it makes it relevant to teach and relevant to apply in a broader context. You have to work a lot harder for that. And anyway, so that's one avenue. Another avenue was that I wanted to. I was pretty always dissatisfied with how the web worked in terms of like this notion that I have to host a web server somewhere, and even to do something as basic as just transmit a set of files, right? Like why can't I just publish this data, and as long as people are interested in resharing it, like have it work on the browser just fine, right? Like not through having to host my own web server. That's another thing. I was interested in BitTorrent like use cases for caching and distribution of content. I was actually pretty excited that we were mentioning Warcraft and StarCraft earlier. Blizzard actually was one of the only companies to use BitTorrent in a meaningful way in their distribution, at least publicly. There might have been others that did it as well, but and it helped solve a big problem with their updates. Like I remember the days when they had all the distribution decentralized, and downloading a patch for a game took forever. Like, and it was also partly the modems that people had, but also just their servers were pegged. So once it moved to BitTorrent, it worked a lot better and faster and much nicer. And that served as an example to prove that even when you're a large company and have a lot of money and so on, you can still gain a lot of value from peer-to-peer distribution systems. So that was like a nice example, right? Skype was another one, I think, for me that really served as a fantastic shining example of the value you get by helping interface and network people in the world, but you're not really an intermediary that they're piping all communications through. I think nowadays Skype does intermediate all of your communications, but that's a whole separate story. I think it has more to do now with the difficulty in connecting people peer to peer, right? Like it actually is pretty hard to open a pipe from one computer to another without having intermediaries. There's a whole bunch of problems like net traversal and so on. That was actually another avenue of this. Was like I was really frustrated with how hard it became to program distributed systems simply because the network was not as nice as IP gave us, right? So IP gave this really, really nice network where everything was addressable. Any computer should be able to talk to any other computer. And then NATs and mobile phone networks and a whole bunch of other things came in to ruin the party, right? Like they made it pretty difficult to open a connection from one process to another.
Right.
Also browsers, right? So like you can't open a socket from a tab, right? Like that's of course a big important security feature, but there are many cases where nowadays applications on the web probably should be able to dial out to anything else. I think the model changes. I think the computational platform of today is more about like the boundary between the browser and the OS is always shrinking. And I think at some point we will want to be able to make that possible. So anyway, all of these things were brewing in my mind. I guess another strong influence was I did a lot of studying of different kinds of distributed file systems. So these are things like Plan 9, for example, which was came out of Bell Labs. Plan 9 had a fantastic set of file systems. It had 9P, which is a really cool protocol for modeling resources in the network as just different pieces in the file system. You use the same pathing to do everything. Ventia and Fossil were two examples of file systems. SFS was another file system that was a huge influence. There are a lot of them. They were all pretty interesting. So I was always annoyed a little bit with a divide between file systems on the web. Like to me, it would be really, really nice to drop into the terminal and be able to just manipulate the web directly, right? So mounted. We tend to use wget and curl and so on, but like imagine if the web was just a directory in your file system and you could like browse through it or read and write through it.
I think zooming out a little bit, I think it's easy to have maybe that perspective now because especially someone like you who grew up in the web, whereas and Jared and I are a bit more of a dinosaur compared to you. I would say that we didn't grow up in the web. Oh, I meant dinosaur. We're older, of course, but we grew up in the age where you joined the web, like that the nodes begin to trickle in, so to speak. Like the web grew and grew and grew, and now it's this big thing. And so it can be easy to look at it now and see, okay, here's the network, it's already there. Here's how we make it better versus where it came from, which was small and got big. So I can see how you can look at it and say, okay, here it is. Let's make it better now that it exists. But you had to build to the point where, like putting a file server onto the web and stuff like that, you had had to stake your claim or put your flag down, so to speak.
Right. I think it's like a matter of perspective, and our generation, which is probably just probably up one from yours, not dinosaur level.
Okay, sorry. My bad.
It's like we saw it come from nothing to what it has become. And so we've seen that change, but we're not quote unquote web native in terms of like growing up inside of what it already was. And so from your perspective, you see it's always, I don't know if I want to say it's always been there, but you're natively understood the web. And so you're seeing how it could be so much better. Whereas perhaps from our perspective, it's already gotten so much better from nothing.
Right.
And so it seems like sometimes it takes the next generation to reinvent things.
To point out the problems.
Yeah. Anyways, so you decided to create IPFS. Can you give the quick high level elevator pitch? We're going to dive deep into it after the break, how it works, the problems you're trying to solve and all that good stuff. But if you had to do like the 30-second, this is what IPFS is, what would you say?
So IPFS is a new way of moving around content on the network. It's a protocol with the goal to upgrade the web and make digital information have more permanence, be able to work offline more, be decentralized, and move around faster in general. So use as much of the power of the network as possible, and change where the points of failure and points of control are. So there's a lot wrapped into it. At the end of the day, it's just to say that it's just software. It's just a new protocol for how computer programs should exchange data. So it's like HTTP in that way. But it's a very different design that borrows a lot of great ideas from other distributed file systems and version control systems like Git. And so it models all content as content that's linked through content addressing and hashes, and uses that as a way of getting a much better security properties and a much better distribution model. So there's a lot wrapped into that. At the end of the day, it's about making the web better, making the web faster, safer, and more secure. And so, there's a lot of, that sounds really nice in the high level, but it's the how this is done and the details that where IPFS really shines.
Well, let's take a quick break and then we will dive into how it shines. You mentioned it exists to make it faster, safer, and more open. In the context of how IPFS works, I think we should keep those three things in mind. And maybe as you tell us the different aspects of the protocol, or I guess the protocol is the right word for it, why this is faster, why this is safer, why this is more open than what we're currently using. But before we go to the break, just from the networking level, where does this fit in? Is it at the IP layer? Is it above IP at the application layer? Where does it replace?
So it is above IP and it's below the application layer. So it complements and potentially replaces HTTP. So think of it as a different protocol for web browsers and applications to use to communicate with each other. And it doesn't exactly fit in terms of the OSI nice network layering model. The networking, the actual layering is much more complicated than networking groups would let on. But it fits there. It's replacing the HTTP layer.
I think that helps just for all of us to be on the same, kind of framework of where we see this fitting into how computers communicate. So I think that's very helpful. All right, let's take that break and we'll talk about how it works in just a minute.
If you're looking for one of the most fastest, efficient SSD cloud servers on the market, look no further than our friends at Linode. You can get a Linode cloud server up and running in seconds with your choice of Linux distro, resources, and node location. And they've got 8 data centers spread across the entire world: North America, Europe, Asia Pacific, and plans start at just $10 a month with hourly billing. Get full root access for more control, run VMs, run containers, run your own private Git server, enjoy native SSD cloud storage, 40 gigabit network, Intel E5 processors. Again, use the code CHANGELAW10 with unlimited uses. Tell your friends. It expires later this year, so you have plenty of time to use it. Head to linode.com/changelog.
All right, we are back and we're talking about the InterPlanetary File System, which, by the way, is just still fun to say.
I love saying that.
I'm gonna keep saying it.
So awesome.
We all know Adam's a big space fan, so I'm sure you're all on board for this name, Adam.
Oh yeah, totally, dude.
But it is a mouthful. So IPFS, its goals are to change the way we communicate with our computers using peer-to-peer distribution protocol, aiming to make the web faster, safer, and more open. Juan, you said that the way it shines is really in the details of how it works. Sounds like you have a lot of education with regard to past file systems, even current file systems, as well as networking protocols. And so you've put together this gem, which people are getting quite excited about. We'll talk about that here real soon. But can you open it up for us and kind of give us a look inside IPFS? Give us the insider look of how it's all put together and why it's faster, safer, and more open.
The core principle underlying IPFS is to model data and link data using causal linking. So this is an idea that goes way back to people like Leslie Lamport and others in distributed systems that talked to us about, or really had a good framing for how to move around data. But more recently, I think distributed version control systems like Git and Mercurial and so on prove to us how valuable it is to model data this way. They weren't the first systems to do it. There were others before, but I think they were certainly the most widely used. And so the same fundamental property that underlies Git, and it's the same fundamental property that underlies things like Bitcoin, is the idea of linking objects using hashes. And so this is both causal linking, meaning that one object is ordered after the other. You can say that when you link something by cryptographic hash, the object that's linking to another has to always come after the other. So it orders them in time. And the other piece of it is that by using cryptographic hashes, you can verify the content. So that if I have a link to an object, right, a file, and that link has a cryptographic hash, it means that I can find that file anywhere. I don't have to go and ask any specific location or authority for the file. Anyone can serve me that file, and I can check that it's the right file because I can hash it and I can verify the hashes match. And so that is an organizing principle for the entire file system that you can build on top of it. And the kernel of the insight for something like IPFS and other systems, not just IPFS, is that if you center on this as the main way to model your data and link the data, then you can make a lot of problems easier. Like you can easily reason about what content came before what other content. You can easily reason about making sure the content is correct and valid, and you can authenticate the content. You can make sure that it's you can verify it's correct, and you are free to now accept it from anyone in the network. Right? You no longer have to go to specific web servers. You can really get it from any other computer. You can also not have to be connected to the internet, actually, right? You can be in a different network that is separate and using and manipulating the exact same set of links. So it is the underlying principle of linking something by hash. We call it Merkle linking, and this comes from Merkle trees. And Merkle trees are a data structure that was invented by Ralph Merkle, a very eminent cryptographer, and Ralph Merkle has done a lot of other amazing things. He one of his perhaps most famous contribution was a thing called Merkle puzzles that proved that you could establish secure communications with each other in the clear. This was before public-private key pairs, so it was like a big important contribution. And this idea of Merkle linking, through Merkle trees, kind of stayed buried in the cryptography community and the kind of low-level systems community for a long time. I think partly because it was patented. I think people were more reluctant to use it, but I think the patent has expired since, and then it began to be used all over the place, including systems like Git and so on. And this is what gives rise to the nice distributed system properties, right? Like you can, when you think about a Git object, you have a hash, you have a SHA-1 hash that you can use to address the commit or address the file or the directory and whatever. And you no longer have to trust the network to provide the correct content to you. And you can reason about the history, right? So you can even talk to the server and find out that it's been compromised because it's serving you some other completely different history. Or maybe it's not been compromised, but people did rewrite history and you can tell that that's happening. And you can be selective about the changes that you take in. So that fundamental property, which is, again, to restate it, you're just linking objects with hashes, right? So you are embedding into one object the hash of the other, gives you this way to tie up content causally, right? So if one object gets updated, then all of the links to it have to change and so on. And this gives you the ability to verify and validate content and to also content address it. So there's another leap there, which is you have to also consider that these hashes may not just be a good way to verify the content, you can also use them as a way to address the content in the links themselves, right? And so you can, you could put it in a file system or in an address bar or something. You can ask for something by hash. This is also an old idea. It's been used in many systems. But by using these simple abstractions and piecing them well together, you can build a distributed system, a distributed information system, if you will, that can move around content in a much safer way because you can verify all of it. It's faster because you can oftentimes check caches that are local to you. It could be in the same machine. It could be in a machine close to you physically, or it could be in the network that you're in, not even having to talk to the internet backbone and so on. So it just makes information distribution faster and allows you to reuse the bandwidth of other peers, right? You no longer have to trust others. You can ask them for something and you can verify that they're giving you the right content. So this is all of this falls out of the fundamental idea of Merkle linking.
You also say here on the website that it combines the distributed hash table that you're talking about with incentivized block exchange, which I'd like you to kind of unpack that for us, and a self-certifying namespace. So let's start with incentivized block exchange. What's that mean?
Yeah, so this is a concept that comes from BitTorrent, right? So one of the improvements of BitTorrent over previous systems was that it modeled data distribution as an incentivized exchange, right? So this means that if you have a bunch of people trying to download a torrent, then it's better for the swarm if people exchange pieces of content that each other needs. This is usually referred to as a tit for tat model. It's not perfectly modeled as tit for tat. So if you ask people in theory and so on, the incentive structure is a little bit different, and there have been better proposals since then. But the basic idea is you say, hey, there's a lot of peers in the network that have content, and anybody can provide the content to you. Select between those peers that are likely to give the content to you, and that becomes more likely if there's an incentive structure there, meaning that if I have pieces of the file or I have pieces of other files that you are interested in, we can exchange those. And that way you align the network so that you share the bandwidth resources, right? So instead of just supporting leeches that are only downloading and not contributing to the network, you get the distribution to sort of, in a sense, not exactly pay for itself, but you help load balance the distribution. This isn't perfect because there's a lot of models where you really just want to transmit data out and you don't really care about people helping share it, or other cases where maybe it's something really big and the people that are distributing it actually I don't know, maybe want to charge money for it or something, right? And so this is something that we took into account when we designed a new protocol called BitSwap, which is a sub-protocol of IPFS. And this is where what we call the block exchange. And so it models the data distribution as kind of like a data barter system where I give data to you, you give data to me, I take into account how much data you've given me in the past, and it makes me more likely to want to give you stuff in the future if you've also given me stuff as well, right? So if our data sharing relationship is profitable, then I am more likely to give you stuff in the future. There's a whole bunch of other cases where maybe I'm new to the network, people should still give me content, or maybe I don't really have anything that other people are interested in that you still have to take into account. And here, the standard HTTP model of I'm just going to distribute out content also works, where you can default back to that kind of thing. And so it's meant more of as an optimization of the network than a hard and fast rule that you force nodes to always distribute stuff, right? There will always be leeches in the network that you have to take into account. And so it's like you're somewhere in between.
So another concept in IPFS is the self-certifying namespace. Can you tell us what that is?
A self-certifying namespace comes from an old file system, not that old, it's early 2000s, called SFS, and that was the self-certified file system. And the basic idea is that, when you think about naming on the network, this is the problem of assigning an identifier to some resource or content that may change over time, right? So, something like foo.com points to an IP address, right? And if I change that pointer to point to something else, how do you know that it was me who did that and not somebody else? right? And so DNS employs, some amount of security in terms of, only allowing certain people to update records. There's all sorts of problems around security of how those records move and all this sort of stuff. But there is a good, amount of security there where it's not like you can, if I own foo.com, then you can't set records on that, right? That's the basic idea. There's other naming systems, right? Like there's other naming systems that work in different ways where, the way that registration happens and so on. Maybe I have a public-private key pair, and so foo.com is bound to, say, a public key. And then any record signed by the private key corresponding to that public key can update that pointer, right? And so self-certifying records or self-certifying file system took it a step further and said, hey, wait a second, what if we relax the constraint and say that we don't need these nice human readable names, and instead just need, we can allow some ugly looking names. What if we just embed the hash of the public key directly into the name itself? And so you can imagine this unreadable name, which is just like a big long hash, but that's just the hash of the public key. Then that means that there's no need for a centralized authority validating or securing the namespace. It's in a sense a distributed namespace that cryptography assigns, right? So this means that by just generating a public-private key pair, I have a name now. And that name is the hash of my public key, right? It's not a nice name. I can't, you can't hear it and type it or anything like that.
Right.
So, name, we tend to think of name as a nice human readable thing. But the value here is that if you relax that constraint, then what you get back is you don't need a centralized namespace. You don't need to talk to the internet to validate a name. As long as you have the records and they're signed correctly by the corresponding private key, then you're good to use the value, right? And so this means that you and I can be in an IPFS network that is separate from the entire internet, and I can create a public-private key pair, and I say, hey, I'm gonna update content, and the link that I give you for that content is, the hash of my public key. Then I can, continue to publish content there, and you can find it, and you can be assured and certified that it was only me that updated that content, nobody else. And so think about it as kind of like and another way to think about it is kind of like a Git branch, right? So in Git, you have immutable content, which are the objects that are all hash addressed and content addressed. And on top of that, you have these mutable pointers, and these are the branches, right? So something like master. And so master is a pointer that keeps pointing to the latest head that you want to consider as master. And whenever you commit, when you say git commit, then you're updating the pointer, the master pointer, to point to the new commit. So the same idea, this is how we use self-certified names in IPFS. They're pointers to the latest version of content, right? So, and this could be a version history, or it could be just one version of the file or something, right? It doesn't matter. You get to decide what that means. But it gives you mutability. It gives you the ability to change content in a completely decentralized way, where you don't have to rely on any central authority whatsoever. This is a huge property. It's a huge win. You end up giving up on the nice human readable naming, but there's ways to add that back in later. You add it on top, basically. Like you map human readability to this non-human readable names, and that are certified, self-certified. And the reason it's called self-certified is that the name itself has the hash of the public key, and that's all you need, right? So if you have the name of the hash and you have the content, you can verify all of it. You do not have to ask any central authority whatsoever for validation. So this means that you don't need CIs, right? Like you don't need CIs, you don't need a consensus-based naming system like DNS. You don't need any of that, and you can just do naming on your own, peer-to-peer. It's a huge thing. This concept shows up all over the place. Lots of systems use self-certified naming. They don't tend to credit it that much, and they don't tend to refer to SFS, which was like the original place where this showed up. But yeah, that's kind of where the idea came from, and it's hugely valuable. And I think people tend to underestimate how important this piece of IPFS is. And there's a lot of challenges that making it scale and making it nicely usable and so on. But it's an important part.
Well, let's pause here. When we get back, we're going to dive into the practical use of IPFS, like how that exists. So far, you've described what seems to be as a bunch of kind of standalone technologies and implementations, data structures, protocols, what have you. We'll put it all back together and see how you can use IPFS, and then we'll talk about who's using it, what they're building on top of it, because it's a file system. So the point is to build things with it. It's not really the end goal, right? It's a piece of infrastructure. So we'll take our break, and after that, we will discuss those things.
Every Saturday morning, we ship an email called Changelog Weekly. It's our editorialized take on what happened this week in open source and software development. It's not generated by a machine. There's no algorithms involved. It's me, it's Jared, and the rest of the Changelog team hand curating this email, keeping up to date with the latest headlines, links, videos, projects, and repos. And to get this awesome email in your inbox every single week, head to changelog.com/weekly and subscribe.
Okay, Juan, so far you've described to us what seems to be a bunch of interrelated yet separate technologies. Can you bring it all together? How does IPFS work? What's the software packaging? How do you use it? How do you get started? Tell us all that good stuff, actually practical uses of putting this stuff out there and using it.
Yeah, so the architecture fits together in that IPFS, the core IPFS node, you don't think about it as a client or a server. You think about it as a node or a peer in the network. We're trying to get rid of the client-server mentality. So you have a node, and this node, what it gives you is the ability to add or retrieve objects into the graph, right? And so the graph is, think of it kind of like the web, but these objects aren't HTML. They're kind of like, and they're kind of like JSON. It's not actually JSON. It's CBOR in the wire format. But they're kind of like JSON objects, and they can represent files, they can represent web pages, they can represent version histories like Git, whatever. And you get to add objects here. So like if you add a file to IPFS, say there's a whole bunch of tools that you can use around IPFS nodes. So for example, you can have a command line implementation, and so the command line tool can add a file, right? And so you can get an IPFS command in your command line that says IPFS add, my file.jpg or something, right? So what that does is that it reads the JPEG and chunks it into a graph, right? And so this means that it'll read the file and split it into a whole bunch of smaller pieces and then construct a graph out of it. And this graph is, you can think of it kind of like the easiest case would be a linked list, but there are some other kind of abstractions. The graph is a description of the file, and here you can chunk really large files this way, right? And it helps version things. And so then you put all of these objects that represent the graph into IPFS, into a local repository. Think of it a little bit like Git. There's some repository in that your node can access where it stores the data. Once the data is in there, the IPFS node is connected to the network, and that network, I'll explain a bit more how it finds the network and so on, but it advertises to the network that it now has this new content added. You don't transfer that content to anyone until they request it. And so this is different from what other people might expect about peer-to-peer systems, but the files don't move unless you explicitly request them. It's an important thing because it means that you're only downloading and accessing the stuff that you explicitly request. You don't have to worry about people adding bad content and it somehow showing up in your node. None of that happens. So and you can also add files through we have this IPFS node can also expose an API, right? Like you can expose an API at an endpoint, and here you can use something like HTTP, or you can use something like a socket, or like a Unix domain socket or something. You just have some way of communicating with it either by command line or programmatically. And you add content to IPFS. And so you chunk it up and you add it in and you link it with these hash links. And now the graph is in your node and other people can access it, right? So say that I get back a link that I can give to other people. And so when I give that link to other people or I place it in an application or something, when those other nodes try to access that link, they connect to the network. They ask the network, hey, who has this content? And they get back a response of a list of peers. And at the very beginning, it may just be one, and then they just contact that peer, your node, and retrieve the content from that peer. And from then on, now that they have the content, they also advertise to the rest of the network that they can distribute it. There are interesting policy questions there where you can also make that optional, right? Like you don't have to necessarily advertise content to the network, or the way you advertise it may be dependent on the use case, right? So certain applications may want to have their own sub network that you're not leaking the content to everyone else. And you can also pre-encrypt the content, right? So nobody, if people end up seeing the content floating by or something, they're not, they're kind of like crawling or aggregating content. They can't read it. They just get this encrypted blob. So that's sort of how you use it, right? So think of it a little bit like Git, where you can add content to a repository, and then now that it's added, it's accessible from any other IPFS node that can talk to your IPFS node. So you form this peer-to-peer mesh network with everyone. And this is where the DHT comes in to help organize how to find peers and access the content and all kind of stuff. There's a whole bunch of interesting peer-to-peer protocols that can come in here. So in reality, IPFS sits on top of a sub-project that we're writing called libp2p. And this libp2p is think of it kind of like as a huge toolbox of interesting peer-to-peer protocols that are useful and valuable in various settings and use cases. And things like local DNS or WebSocket transports or WebRTC transports and so on. And you're able to piece these together into a nice connectivity fabric that we like to term like the peer-to-peer network. And your IPFS node just sits on top of that and is able to find other IPFS nodes that have the content, and they retrieve the content, and now you can survey it, right? So anyway, long story short, the basic idea is, from an interface perspective, you add content to IPFS, and once it's added, it's only in the node that you added it to. But then you can move that link or give it to other nodes, and they can then pull the content and move it elsewhere. And now it's distributed to more than one node, and all of those nodes can now help share it. So it's a little bit like a BitTorrent in that way.
Can you just put it up there and say, give this to all nodes or any nodes? Like, do you have to be specific around which nodes that you're going to distribute through?
You can, other nodes can, and this is something that we're still working on and figuring out exactly how to do, because there's many different constraints here, right? The hard constraints here are that we can't make it so that you, by writing to IPFS, somehow get to send content to other people. Because that content could be bad, right? So imagine that you have some illegal content of some sort and you add it to IPFS. That content should not automatically be sent to other people. That should just be on your node. And it's only by other people requesting it that you move it, right? And so,
plus you could easily DOS their server if you just fill it with more content than disk space they have, or it just seems like there's lots of bad things that could happen that way.
Exactly. So it's kind of like a pull model, right? And so what you can do though is, once you add content, you immediately send a message to another node saying, "Hey, I just added this content." And if you can have some authenticated agreements, like saying, "Hey, please replicate all content that I have," right? And so you can think of it a little bit like git pull and git push, right? So most of the functionality is pulling, and pushing has an authentication that needs to be in place, right? Like you shouldn't be just allowed to push to any arbitrary node. They have to sort of allow you to do this. And both of these may be your nodes. You just need to make sure that the system knows that that's possible. And so given some authentication, then you can push objects however you want, and distribute them to other nodes. But then they're sort of available. So think of it kind of like one massive BitTorrent swarm that's moving around objects in one massive Git repo. And all of the objects there are accessible to your web browser, so that your web browser can directly fetch content from this repository of objects. So you can put images, put web pages, put whatever, and you can now access them all through the browser.
Seems like it'd make it pretty trivial to build your own private Dropbox in terms of you just build the authentication around which computers can act as nodes.
It's authentication and some UI like user experience stuff.
Exactly.
We're playing around with some of that. We're more interested in the lower level protocol stuff, but there is a file browser thing that we're making that's pretty cool actually. Like you can drag and drop files in the browser, and it adds them, and you can view them and send them to other people and so on. There's a lot of interesting challenges around sharing links and encryption there that we're working towards. We don't have all of that stuff in place yet. We'll be doing that over this year and in the coming months and so on. Different groups are very interested in this. And so right now we're kind of focusing on getting the perf to be really good and
Right.
focusing on the public use cases, but all the private stuff is just around the corner just by adding encryption.
Yeah. So it sounds like, I look at this, anything that's a file system, whether it's distributed across all these nodes or if it's just sitting on my little laptop right here, it's a building block, it's a part of a bigger system, right? And so it seems like what you guys want to do is lay a really good foundation and have all of these different aspects of things that you would want to build on top of it figured out so that they're possible, and then let people go nuts. Um,
Yeah,
what are
exactly.
some applications that you guys see being built on top of it? I just mentioned an idea of like your own personal Dropbox type thing. One thing that hit our radar recently was this everythingstays.com, which was a immutable and distributed Node.js modules. Seemed like it was a package registry built on top of
Mhm.
IPFS. What are some ways that people are interested in using it or even possibly using it currently?
IPFS is meant to just interface with the web of today directly, right? So
Yeah.
it's meant to just kind of rebase the web on top of this better protocol for moving around content. So we're doing a whole bunch of work to make sure that IPFS is uh, accessible to people using web browsers today, and that web developers don't have to think about a new model. They're just doing the same kind of web applications that they're building today, but just on IPFS, right? So you can do pretty much anything that you would build on a web app now on top of IPFS. It just depending on how content updates, you might think a bit of it a little bit different, and depending on how you want to do control, you might think of it a little bit differently. So let me give you some like concrete examples, right? So you can do file distribution really easily, right? Like this means just add static files, right? Any kind of static file delivery. So CDN use cases and so on. That's pretty easy. The next thing on top of that is things like package managers. So you mentioned everything stays. IPFS began its life as a package manager itself. So the original goal was to make a dataset package manager, right? So add the nice versioning features that we have around Git and the nice distribution system of like something like BitTorrent and make it usable for moving around scientific data. Then I just kind of realized that this would be really valuable for the web as a whole. So, really just focused more on that. And the thing here is like a package manager for code like npm or a package manager for binaries like aptitude or something are all very similar. And when you add hashing to how you make all of those links, you can decentralize the whole thing. You can think of package managers as moving around all of these static pieces of content, right? Whether it's code or binaries, and you can address all of those by hash. And so you can think of making a completely decentralized package manager on top of IPFS. And in fact, IPFS makes it extremely easy to do all of this. And so you can look at, we have one package manager called GX that you can take a look at. It's our solution for package management in Go. And we use it to build IPFS. It's a little bit, pretty opinionated, and it's early days still, but it's super exciting. So check it out and, think about it. And yeah, of course, there's a bunch of things coming around npm, like everything stays and other systems, right? So we actually favor using. We were doing one where we are importing the entire npm registry into IPFS and still using npm, as a centralized registry for the naming, but have all of the content be addressed by hash and distributed peer to peer, so that you can, when you npm install, you could download the files from other computers that are near you, right? So imagine that you're in an office setting with like 50 other people or something, and you're npm installing something, and you know that you've downloaded this stuff before, or that other people in the same room have downloaded it before. There's no reason you have to go out to the backbone of the internet and download it again. And so you can dramatically speed up all of this, or maybe even make it work completely offline, right? So imagine that the connectivity in your office falls apart, and suddenly you can still install all these npm modules because you already have them. Somebody has them in your office.
How do you know about versioning at that point? How do you know you're getting the latest version or the? Is it too late to ask that question? I mean, that's what I think about when you say stuff like that.
It depends on how the caching and the updating of the versions happens, right? So one model here is that the registry, so the index of versions, right? So like how the name maps to a list of versions
Right.
that have been published, that itself you can download and cache, and that's not very big. So you could cache all of that pretty quickly, and maybe you can't get the latest version that was published right now, but you can get the version that was published an hour ago, right? Or whenever, right before when the internet went down.
Right.
So you can think of accessing data as not a strictly online procedure that happens at that moment, but rather this kind of like more asynchronous thing where everything is sort of more eventually consistent. That's one way of looking at it. It's not a strictly eventual consistency; it's a different property. But
And I guess the push-pull process provides the authentication to trust.
yeah, exactly. So well, you have the hashes, right? So you have the hashes and they're signing for updated for mutable things. There's you can sign them directly, right? So npm can sign the registry and the updates to the registry and distribute those, so you know that they're valid.
Right.
And
Okay.
even in another more decentralized way, like you wouldn't, then the individual authors could sign them, right? Like the individual authors could sign it with their key, and it's a valid new version.
Just think about trust in that situation. Like if I can bypass the backbone of the internet and trust local network, even if it's an older version, what allows me as the user to feel comfortable to know like, well, hey, I'm offline, but I can still trust what I'm getting.
Yeah.
And that's what I think.
So
about.
you can do things there like there's a whole bunch of interesting challenges that are more application dependent. On something like a package manager, what you would want to do is expose what versions are available. And then you have to know that these are the only versions available in the network that you can see right now, but the new ones may have been published, right? And so you can attach dates to that and know when they were published. So if you think that there might be newer stuff, then you know whether to use them or not. So there's some interesting challenges there, but we can think about data in a more distributed sense and offline first. So these are the same kind of questions, by the way, that people were wondering about Git at the beginning, right? So when Git was getting started, everyone was really worried. They're like, wait, what do you mean I can just ask somebody else's repository for the data? Like, don't I have to go to like the central server? And the reality is no, you can make sense out of all of these pieces of information. The central server is really good to maintain, the latest copy or the latest, have some notion of what the latest value that we want to agree on is. But you can get the pieces of data from anyone. And even those updates can be distributed through peer-to-peer. Cool. So yeah, package managers are another great use case. One really exciting use case that we like a lot is distributed chat, right? So we use IRC to, we have this IRC channel, #IPFS, come hang out, to communicate and so on. But we also would like to be able to chat when we are, say, disconnected from the internet. Like, for example, if we're traveling together and we are, I don't know, in a train or maybe just in some poor connectivity location, we would like to be able to chat. And things like IRC or even things like Slack and so on don't work in that use case because you have to connect to the backbone, right? And all of the messages are sent through this backbone. But what if you could have a chat room that just works wherever you are with the peers that are around you? And so that's where we're creating a thing called Orbit. And Orbit is a peer-to-peer chat application. It's all entirely on top of IPFS with dynamic content. And the way it works is that all the messages are individual IPFS objects. You have a message log that points to all the data. So you can think of it a little bit like a blockchain sort of. It's not a blockchain actually. It's a better data structure. It's called a CRDT. CRDTs are a class of data structures. They're amazing. I could probably spend whole days talking about them, and I highly encourage you to have a future talk and interview about CRDTs with some of the CRDT experts out there. But it's a really good way of modeling data, and IPFS allows and supports building CRDTs on top of it.
What's it stand for?
CRDT stands for, depends on who you ask, it actually stands for a couple of different things. So it could be convergent replicated data type or conflict-free replicated data type or commutative replicated data type. And I think there's a different version for the R too. They're all different words for expressing the same set of principles. They, depending on which one you use, the emphasis and the implementation changes. So the systems actually look a little bit different depending on what you call them, but the basic principles are the same, and the constructions are isomorphic, meaning that you can build the same kind of stuff on top of each other, and they give you the same properties. So what these mean is that imagine if Git had no conflicts, like never had any kind of merge conflicts, right? So this is more like you're used to, say, like Google Docs, right? So Google Docs uses a thing called operational transforms, and this means that when you make edits on a Google Doc, all the operations are guaranteed to never conflict. That means that they can commute or in the end converge. So they're all convergent. You can apply them in whatever order and you achieve the exact same result. CRDTs are a better version of operational transforms, or at least you can think of them that way. It's a different, research lineage, but they're used for the same kind of stuff. And you can do things like Etherpad type of data structures, but you can also do something much more general, like a chat application, or even something like a whole social network or email and so on, right? So it's a really striking new distributed systems type thing, and super valuable research that is just now being turned into applications. And so we built a whole chat client using CRDTs on top of IPFS. And it's really cool, right? Like you can just load it up and start chatting with other people on the IPFS network, and all of the content is moving through IPFS. So a lot of people were wondering, hey, IPFS is really cool for static content, but what about dynamic content? And yeah, we can do that too. The secret of making it fast there is we use PubSub. So this is the one piece that we're still, it's not fully there on the public release of IPFS yet, but we're still working on the interfaces and how that will work. But yeah, PubSub, making it possible for some IPFS nodes to move around content to each other really quickly is a big part of making this work really nicely. So going back to the office setting, right? Imagine that you're talking to each other in your team chat, right? And so imagine that the internet connectivity falls apart, right? Like you should still be able to talk to each other. You still have computers. You still have a network that works in the building. Like, why is it that you can't talk to each other, right? Like that's just a very silly problem. And so we IPFS is meant to solve all these kinds of problems, like decentralizing the web, right? So one of the fundamental problems with how we're using the web today is that websites and links in the web, or all the content and APIs and so on, the way they work is that they force you to go to the backbone and talk to people in the backbone to make sense of the data. And this creates this huge central point of failure, both central point of failure and central point of control, that those websites own that data, and if they disappear or they cancel the service, or they're just inaccessible because the links between you and them are failing, suddenly you cannot use this application, right? And this is a deeply unsettling problem, right? So on the surface, it's like, well, they're providing a service, and usually, a lot of times for free, but sometimes, you pay them, and it's a best effort service, right? And so if it doesn't work because there's a major disaster or something, well, tough luck. But at the same time, most of our communications are starting to be moved through the web, right? So think about how you talk to your coworkers, or more importantly, your family members, right? So you probably use some chat system. And if you're using this chat system and there's some disaster or something, or just a service falls apart that day, suddenly you can't talk to them anymore. And now this superpower that you had, this amazing ability to just talk to them really easily and quickly, is gone. Like, immediately, like surprisingly, suddenly. And so we need to, as engineers, restructure how we build web applications to make sure that this is not a problem. That we build resilient and decentralized applications so that these messaging platforms should be able to continue operating even in those cases, right? If the internet works, right? If I have the ability to have my computer contact yours, that should be enough to be able to communicate with you. And this happens for messaging systems. It happens for web applications. It happens for chat systems in general, things like GitHub and so on. I recall GitHub has been under a lot of attack in the last couple of years, right? Like last year, it was taken down by a CDN problem, right? Somebody injected some bad code into a CDN, and which caused a lot of people to attack GitHub, right? And even earlier this year, it was taken down again by some other problems. So suddenly, in those times, a whole bunch of people were, kind of frustrated by the centralization of GitHub, and said, "Hey, why don't we just like decentralize GitHub and have it work over something like IPFS, right?" And
Right.
it turns out that like IPFS could actually help tremendously in this problem, right? So on the first hand, if a CDN was using something like IPFS, that initial attack vector would just not work. The attack that people did last year of like injecting some code into the CDN would just not happen at all, because all the code would be certified and checked, by hash. The second part is that even if you manage to attack GitHub and take it down, if you were properly decentralized, then other peers that have the content can help serve it. And so it doesn't matter if you take one host down. Other people should be able to serve the same exact content. And maybe it's a little bit slower or something, but the important part is the content is still there. And so this is one of the important parts of decentralizing the web, right? So IPFS in a big way is becoming a big push to make sure that the web itself is decentralized. And the thing is that there are certain problems when centralized websites impose a point of failure and a point of control. And so if we use a better model of moving around the data, then we can, save ourselves from these like deep problems of the web, right? Like we can make it more resilient. We can think back around actually like controlling more as a user where the data ends up and who uses it and who has the ability to address it, right? So one way of summarizing, in a big way, what IPFS is about is like, imagine when you cite a book or you go and find a book. Imagine that people told you that the only way that you could find a book is by giving you a bunch of directions of how to find it at a specific library. And suppose that you live in, I don't know, New York, and they tell you that to find this book, you have to go to San Francisco, and you have to go to a specific library in San Francisco and get a book there. And like that's the only possible way of reading this book. And it's really silly, right? Like why couldn't you just get an ISBN number or the title of the book and look for that book elsewhere in a different library? And like that's what IPFS is about. It's about making it possible to get the content from whoever has the content and making digital information move like physical information, right? Like where you can get a copy anywhere, and you could get, as long as somebody has the copy to give you, you should be able to get it and use it. And this has vast, deep implications for how content moves, how resilient the network is, how applications operate on top of it, and the points of control around the data, right? So imagine if I could give you a link to it. So suppose that people use things like Twitter or Medium to publish a lot of their thoughts, right? And this is really valuable forms of expression that people have. Like a bunch of important communications happen over these networks. So imagine that those services go away, right? And suddenly all of those posts or tweets or whatever disappear, or all of the links at least break, right? So even if you can download data or something, the links will break. But what if instead you could, when you add data, you could get a link directly to the data itself, not going through an intermediary, not going through twitter.com, but rather going directly to the tweet and being able to order the Medium post, right? And being able to move that around without having to trust that these organizations will continue to exist decades from now.
Yeah. I was going to ask you the question on what you had said in your talk at Stanford, the future of the web could be in danger, but it sounds like you've pretty much answered that by these examples of, the danger of the future of the web could be that without decentralization, we kind of give up control, as you said, to these networks. And whenever they decide to go away, whether it's because there's an internet outage or a connectivity issue or, something more serious like a business issue, and let's say Twitter fails, as a business and goes away, you've got all this collective effort that is all this expression, as you had said, which is valuable, that just now goes away. And so is that what you meant by the future of the web could be in danger, by the fact that if we don't think about decentralizing content networks and data networks like that we could be giving up too much control, and there's a way we can actually build in the security and control for the long term by leveraging IPFS?
Yeah, exactly. Right. So these are important concerns about how the data that we create and publish moves through the network, right? And how we address the data is a huge part of this, right? Today in HTTP, we address the data through a DNS domain name, which maps to an IP address, and that means a specific location on the network, right? It means a specific set of computers, usually controlled by one organization. And whatever happens means that like that domain name could, that business could go away, that organization could go away, that service could be canceled. Think about how many services have disappeared, and you suddenly wake up to a notice one day and that tells you, hey, the service is now been taken. It's going to be taken down in a month. You have 1 month to take all your data and move it elsewhere, right? And like, what about all of the links that you gave to other people, right? Like suddenly all of that breaks. And so we are, tired of that kind of model, and we don't think that that's at all, ethical, first of all, or correct to. There's a whole bunch of concerns. You can't force people to continue providing a service that they just can't in terms of a business. Like that makes sense, right? But there are ways in which we can model how to structure and link to the data such that it doesn't matter if that service goes away. The data is still there, and the data can still be accessed, and the data can still be backed up, right? And so like that's a big part here, like making sure the links don't break, making the links be able to last in the long term.
Gotcha.
And so. Yeah, it's a lot of this, as part of the archival efforts as well, right? So think about being able to archive all this content.
Building it into the way the network works is, if it's built in, you don't have to really think about it. It's just part of the way the file system works. And, we could be in an age where, 5 years down the road, this has gotten more widely adopted and more networks use it. And then, it might even take over a larger portion of what we know as the web today. And it's built in, and you don't really have to think about data being lost or networks closing or a file not being there, because it resolves no matter what, given the protocol.
Yep, exactly right.
Well, one, it was definitely a fun deep dive into this topic. I know that interplanetary travel is fun, and so are file systems. So why not combine the two? I had to put that joke in there, and I swear, Jared, I kind of wish we could play the Beastie Boys. They probably sue us though, which is a shame. Because I want
fair use. You just got to keep it short.
Oh, you got to keep it short. And I did some looking up that IGFS is while it may not be suitable, there's still time to change. So I mean, you could change to IGFS.
Maybe for April Fool's Day next year, we'll rebrand everything.
There you go. There you go. Well, Juan, anything else you want to mention before we close the show? We got about 2 minutes to close.
Yeah. I think, first of all, thank you very much for having me. This was a really exciting discussion. There's lots of stuff to talk about. The project is really, really big. I wanted to give, first of all, one huge shout out to the entire IPFS community that is building this out, right? So this is not, this is not really my project anymore, right? Like this is a project that everyone owns, right? Like it's a huge, large project with lots of people contributing, lots of people making it happen, lots of ideas. I get to sit here and represent other people, but there's some amazing contributions from all sorts of people around the world. And with that, our open source community is super open, right? And there's open source and there's like open source, and we're like open source, right? Like you can come in and tell us, please, file bug reports and all that kind of stuff, but also tell us, what you would like to see, what features you would love to, have, like if anything needs more documentation, like come and hang out in IRC. Come and contribute on GitHub. This is IPFS will become what you make of it, right? Yeah. And so it's a big call to people out there to come and join us and help remake the web in a much better and decentralized way. So welcome, and everyone's welcome, and we definitely look forward to the project growing and so on.
I'm looking forward to seeing some listener pick this up and email us back with something they created using it. And then that way the complete circle can be made. And then we can have them on the show talking about how they leveraged IPFS to build the next big thing or whatever. Because that'd be the best way to do it, right?
Yep.
So listeners out there, we thank you for tuning into this awesome show on rebuilding the web, basically, and omitting some danger that could be in our future if we don't decentralize. So if something has been interesting you about networks that this problem has been there, but now IPFS solves that problem, then go build it, or at least think about it and share that back with us and tell us what you think. But Juan, thanks so much again for joining us today and covering this conversation. But that's it, fellas. So let's call this show done and say goodbye.
Goodbye. Thanks, Juan.
Yeah, thank you very much. Bye.